So let's look at a direct application of Lagrange's theorem. The group of integers modulo 8 under addition modulo 8 does not have subgroups of order 3, 5, or 7, since 3 does not divide 8, 5 does not divide 8, and 7 does not divide 8. Now the entire group is generated by the element 1 and is also generated by the additive inverse of 1, which is 7. The cyclic subgroup generated by 2 is also generated by the additive inverse of 2, which is 6. And this is the group which contains the elements 0, 2, 4, and 6. The cyclic subgroup generated by 3 is also generated by the additive inverse of 3, which is 5. And this is the group which contains the elements 0, 3, 6, 9 modulo 8, which is 1, 4, 7, 10 modulo 8, which is 2, and 5. This is the entire group. And the cyclic subgroup generated by 4 is the group which contains the elements 0 and 4. So if we look at the subgroup diagram, the integers modulo 8 has as a proper subgroup the cyclic subgroup generated by 2, which has as a proper subgroup the cyclic subgroup generated by 4, which has as a proper subgroup the trivial subgroup. If we look at the orders of these groups, we have 8, 4, 2, and 1. Now, since the group of integers modulo 8 is cyclic, each of its subgroups are also cyclic, and so these are the only possible subgroups. And the orders of these subgroups divide the order of the group. So as a second example, the deleted set of integers modulo 8 is the group which contains the elements 1, 3, 5, and 7. And this is a group under multiplication modulo 8. And this group does not have a subgroup of order 3, since 3 does not divide 4, which is the order of the group. Now if we look at the subgroup generated by the element 1, this is the trivial subgroup. The subgroup generated by 3 is the group which contains 3 and 3 squared, which modulo 8 is 1. The subgroup generated by 5 is the group which contains 5 and 5 squared, which modulo 8 is 1. And the cyclic subgroup generated by 7 is the group which contains 7 and 7 squared, which modulo 8 is 1. So if we look at the subgroup diagram, the deleted set of integers modulo 8 has 3 subgroups of order 2, the cyclic subgroup generated by 3, the cyclic subgroup generated by 5, and the cyclic subgroup generated by 7. And each of these has as a proper subgroup the trivial subgroup. So just as with the Klein-Fear group, the group of deleted integers modulo 8 under multiplication modulo 8 is a non-cyclic abelian group. So let's look at the Cayley tables for these groups. Now in the Klein-Fear group, each element is its own inverse. And A times B is the same as B times A, which is C. A times C is the same as C times A, which is B. B times C is the same as C times B, which is A. And in the group of deleted set of integers modulo 8 under multiplication modulo 8, each element is its own inverse. 3 times 5 is the same as 5 times 3, which is 15, which modulo 8 is 7. 3 times 7 is 21, which modulo 8 is 5, and this is same as 7 times 3. 5 times 7 is 35, which modulo 8 is 3, and this is the same as 7 times 5. So notice that the Cayley tables for the two groups are identical, and so the group of deleted integers modulo 8 under multiplication modulo 8 is isomorphic to the Klein-Fear group, and an explicit isomorphism is a bijection mapping the element 1 onto the identity element E, 3 onto the element A, 5 onto the element B, and 7 onto the element C. Now, Lagrange's theorem has some interesting corollaries. Every group of prime order is cyclic. So proof. Let G be a finite group of prime order P, and let the element A be an element in the group where the element A is distinct from the identity. Then the cyclic subgroup generated by A has at least two elements, namely the identity and the element A. And so the order of the cyclic subgroup generated by A is an integer m, where m is greater than or equal to 2. Now, by the previous theorem, Lagrange's theorem, m must divide p. Now, since p is prime, the only positive divisors of p are 1 and p itself. And since m is greater than or equal to 2, m is not equal to 1. And hence, m must be equal to p. That is, the cyclic subgroup generated by A is the entire group G. And thus the group G is cyclic. Now, since every group of prime order is cyclic and every cyclic group is abelian, we also have that every group of prime order is abelian. So, new definition. Let G be a group. The order of an element G in the group is the order of the cyclic subgroup generated by that element. And so as a second corollary, we have that the order of an element of a finite group divides the order of the group as proof. Let G be a finite group. And let G be an element in the group. The order of the element G is the order of the cyclic subgroup generated by G. Now, since the cyclic subgroup generated by G is a subgroup of the finite group G, once again, by Lagrange's theorem, we have that the order of the cyclic subgroup generated by G divides the group, the order of the group. That is, the order of an element G in the group divides the order of the finite group G. So let's look at an example. Let's look at the subgroup diagram for the group of integers modulo 4. This group has as a proper subgroup the cyclic subgroup generated by 2, which has as a proper subgroup the trivial subgroup. The entire group is generated by the element 1 and also by the additive inverse of 1, which is 3. If we look at the orders of these groups, we have 4, 2, and 1. So notice that the order of the element 0 is 1. The order of the element 1 is 4. The order of the element 2 is 2. And the order of the element 3 is 4. And the order of the elements in the group divide the order of the group. So new definition. Let H be a subgroup of a group G. The number of distinct left cosets of the subgroup H in the group G is the index of the subgroup H in the group G, and this is denoted this way. So notice that if the group G is finite, then the index of the subgroup H in the group G is finite. And in fact, the index of H in G is the order of G divided by the order of H, since each coset of the subgroup H has the same number of elements as in the subgroup H. So let's look at an example. Consider the subgroup, the cyclic subgroup generated by 2 of the group of integers modulo 8, the index of the cyclic subgroup generated by 2 in the group of integers modulo 8 is the order of the group of integers modulo 8 divided by the order of the cyclic subgroup generated by 2. And so this is 8 divided by 4, which is 2. And so there are two distinct left cosets of the subgroup, the cyclic subgroup generated by 2. And those are the left coset containing the element 0. And this is the entire cyclic subgroup generated by 2. And so this is the set containing 0, 2, 4, and 6. And we also have the left coset containing the element 1. And this is the set containing the elements 1, 3, 5, and 7. So as an exercise, find the index of the cyclic subgroup generated by 3 in the group of integers modulo 24 and find all cosets of the cyclic subgroup generated by 3. So next we'll prove a theorem. Let K be a subgroup of a group H, which is in turn a subgroup of a group G. Suppose that the index of K in H and the index of H and G are both finite. Then the index of K in the group G is finite, and the index of K and G is equal to the product of the index of H and G with the index of K and H. So proof. We can show this by direct computation. The index of K and G is the order of G divided by the order of K. This is the same as the product of the order of G divided by the order of H times the order of H divided by the order of K, which is the index of H in G times the index of K in H.